Good morning, guys, and welcome to our nice new shiny topic, organic chemistry. We're going to go through some of the basics of what organic chemistry is, what a homologous series is, and how to represent some of the molecules, some of the drawing and things like that. So let's get going. Okay, guys, so what is organic chemistry? Organic chemistry is essentially the study of how compounds that are made of a majority of hydrogen carbon, particularly carbon, we're studying how they behave, how they react, how we could produce them, or how we can convert them to other compounds that are also in the organic chemistry family. So it's basically the study of any chemicals that have a backbone of carbon. They're made mostly of carbon with hydrogens, usually a little bit of oxygen, nitrogen, and so on thrown in as well to make things up. We group these organic chemicals into things called a homologous series. So homologous, homo means same, logos means sequence. So homologous is a same sequence. So a homologous series are chemicals that have these 5 properties. So they will have the same functional group. Now, functional group is the part of the molecule that does reactions, and we'll talk more about functional groups as we go through the course. And they perform the same chemical reactions, mostly because they have the same functional group, so they're going to do the same reactions because they have a similar section on their chemical. They have the same general formula, which is something we're going to talk about when we get to each of the homologous series separately. But it basically means you can mathematically work out if a chemical belongs to a series using the general formula. They have a trend that gradually changes in their physical properties. So, for example, their melting points may slowly increase as you get to bigger members of the homologous series. The colour may follow a pattern, kind of like the group 7s get darker as you go down the group. An organic chemistry homologous series will have a pattern in how the colour changes. And then the last one to spot is that to reach the next member, you add an extra CH2 to the molecular formula. So they get longer by 1 CH2 unit each time. So first of all, we're just going to look at hydrocarbons. Now, this is a really important definition. They like to ask this a lot in the exams. So it is worth recognizing hydrocarbons are organic molecules that contain only, in big letters and highlighted, only hydrogen and carbon atoms. So if you have any other kind of atom in there, oxygen, nitrogen, it is not a hydrocarbon. It could still be an organic molecule, but it is not a hydrocarbon. There are 4 homologous series that are hydrocarbons. You guys only need to worry about 2 of them, the alkanes and the alkenes, which will be our next few lessons. We'll take a lesson looking at alkanes, we'll take a lesson looking at alkenes and how they're different from one another. But just for reference, in case you want to know, the other 2 are called alkynes and aryls, but you won't need them for any of this. So we've got our hydrocarbons. The first thing we need to be able to do is a bit of naming. So all of our organic molecules have 2 parts. They have our carbon chain, how many carbons they are, and they have this functional group, the thing we said that helps you decide which homologous series they're in. The first part of any organic molecule's name tells you the number of carbon atoms. Now this bit you're going to have to learn. When we look at alkanes, I'll get you to write a little mnemonic to help remember these, but this is just a general intro at the moment. And the second part of the name tells you which functional group, which homologous series the chemical belongs to. It's kind of like, as it says, a first name and a surname. The first name tells you how many carbons there are, the surname tells you which family it belongs to. So we have particular names that fit for the number of carbons, and you'll recognize some of these. So meth, eth, prop, bute, pent, hex, and if you wanted to guess, they carry on almost like in maths do with shapes. So 7 is hept, 8 is oct, 9 is non, 10 is dec, like the shapes and the number of sides. But you need to know these first 6. So you're going to have to memorize the meth, eth, prop, bute, pent, hex section. Lots of people have different ways of doing it. There's Miss Ellis Punches Boys is one that I've heard. There's Monkeys Eat Peanut Butter. Most people struggle with the first 4 because once you get to 5, pent, pentagon, hex, hexagon, you can tend to remember them. But we'll do some more work on these later. The second part of the name tells you which homologous series they're in. So that we've already mentioned the alkanes and alkenes. So an alkane would end in ane, an alkene would end in ene, alcohols end in anol. So we've heard of ethanol, that would be because it's got 2 carbons and it's in the alcohol group. Then the other 2 you will come across later in the course, carboxylic acids and esters, also have an ending that lets you spot them from their name. You'll have all heard of methane before in terms of global warming gases and things like that. It just tells you how many carbons are in it and what functional group, what homologous series it belongs to. Now, on to the representations. How do we draw these things? We've looked at some different groups and different definitions, things like that, so now we need to have a little look at some different ways to represent things. So there are a few different ways we can represent organic molecules. Now, in the first place, the one you will be most familiar with is what we call the molecular formula, which is where we write down the actual number of each type of atom in the molecule total together. So if we had a molecule that had a molecular formula of C2H6, for example, we know that that molecule has 2 carbons and 6 hydrogens in it somewhere. Or we could have C3H6, so we know that molecule would have 3 carbons, 6 hydrogens. We don't know anything about how they're arranged. Okay, all it does is give you the total. It's very good for calculating the MR, which we've done in previous topics, so this is useful for working out the MR. But you can't tell which families necessarily these chemicals belong to, because you don't know how anything's arranged in them. You don't know what functional group they may have. You could have things that are completely random shapes. Let's say we had something that was C8H18. There are lots and lots of ways you could arrange 8 carbons and 18 hydrogens, still sticking with rules of carbons need 4 bonds, hydrogens need 1 bond. So the molecular formula only really tells you how to work out the MR and what you have in total. It doesn't give you any idea of the actual shape of the molecule you're dealing with. From that, we can often work out the empirical formula, which is just our simplest ratio of atoms in the molecule. This will become really important next year when we look at how you can calculate empirical formula from experimental data, and then you can turn empirical formula into molecular formula if you know the MR. But at this point, all you need to know is the empirical formula is the simplest ratio of atoms. So we could take C2H6, and our empirical formula would be CH3. Because for every 1 carbon, we have 3 hydrogens, so that would be the simplest ratio. So our C3H6, obviously we can divide both by 3, so the ratio would be CH2. That would be our empirical formula. For this one, our empirical formula divided by 2, we would get C4H9. So that would be our empirical formula for this one. Now sometimes they could be identical, the empirical formula and the molecular formula. So for example, C3H8 cannot be simplified down. That is the simplest formula. So its molecular formula and its empirical formula would be identical to one another. Our next type of representation is called the full displayed formula. Now, the problem we have with the molecular and the empirical formula is it tells you nothing about how the atoms are arranged relative to one another. The full displayed formula fixes that problem because it shows every covalent bond between all of the atoms, so every atom in the molecule. Very key when you're doing a full displayed formula is to remember that carbons have to have 4 bonds under all circumstances, and hydrogens can have 1 bond under all circumstances. You can't break this rule because of the number of electrons they can share through covalent bonds. So carbons are always going to share 4 electrons out to get 4 back to get to 8, so they have to have 4 bonds. Hydrogens only have 1 electron, so can only share 1 electron, so can only make 1 bond. Now, full displayed formulas you will have seen before. This is the one where we show every single molecule, every single bond in the molecule, and we draw it out big and complicated. So let's take a look at the 4 molecules, the 4 molecular formula we used earlier, what they would look like in full displayed formula. So C2H6, we would have our 2 carbons joined by single covalent bonds, and then our hydrogens arranged around the outside like this. So the carbons have 4 bonds, each of them, and the hydrogens have 1 bond each. And we've shown every covalent bond in there. C3H6 will be a little bit trickier. We have 3 carbons, but only 6 hydrogens. We can't put a hydrogen all the way around each of these. This is because it's in one of our different homologous series. We're going to talk about the difference between alkanes and alkenes over the next couple of lessons. But it does mean we have double bonds. So we would have 2 lines drawn in between, so that each of our carbons has 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, and all of our hydrogens have only 1 bond. C3H8, so this one has enough hydrogens to go all the way around, so we could draw each one out individually, nice and easy. And then we could have C8H18, which 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes. And then 18 H's. Now, as you can see, this formula or this style of representation gives us lots and lots of detail. We can see everything going on. But when we get to the bigger molecules, it gets very, very, very tedious and long to draw. So we obviously have some simpler versions that you can use that still show you the structure but don't require quite all of this long drawing. Something to note, you can also have something called a 3D displayed formula, which you may come across a little bit. This just shows the real shape around the bonds, which we can look at with Molymod and things like that when we get into different bits of school when we get back. But basically, instead of the flat 2D drawing, it just shows that the hydrogens, for example, in our molecule are not in the plane of the paper. So the 2 with the big wedges are coming towards us, the 2 with the dashes are going away from us. So it just gives you an idea of the real shape of the molecule. Something that's worth noting, carbons always make a tetrahedral shape because they have 4 bonds, so they can stick out to make a tetrahedral shape. As we said, our full display formula can be a little bit fiddly when we get to our bigger molecules. So one of the simplifications we use is what's called the structural formula rather than the displayed formula, which shows each carbon section of the molecule in a simple format. So what do I mean by this? So if we take our full displayed formulas from earlier, we have our C2H6 here. We can write down what each carbon segment would represent, so then we still know the shape of it. So for example, that my first carbon segment is a CH3. Okay, that's what's attached to that first carbon. So we would write CH3 as our structural formula, and then my next carbon segment is a CH3 as well. So my structural formula for my C2H6 would be a CH3 attached to a CH3. So we could do this for each of our molecules. So my first carbon segment in this case is a C with 2 H's on it. So it would be a CH2. My next carbon segment is a CH. So I would just write CH. And then my last carbon segment is a CH3. Now, because we know that all carbons have to have 4 bonds, because there are only 2 hydrogens on this carbon and 1 hydrogen on this carbon, we know they must have a double bond between them to give it away. So we still know the structure because we know carbons have to have 4 bonds, so we can still work them out. So then if we had our C3H8, we would have C3H8 would be CH3, CH2, CH3. Okay, because we would have our CH3 block, our CH2 block, our CH3 block. Now this makes it much quicker when we get up to our big molecule, our CH18, because we can now go CH3, CH2, CH2, CH2. So we could write it out as CH3, that's our first carbon, then second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon, seventh carbon, eighth carbon. which is much quicker to write out, and it still shows the same thing, CH3, CH2, 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 but it's quicker to write out than drawing all the bonds in between. We can also simplify this down a little bit, which you will sometimes see on test papers. We can simplify it down a little bit to CH3, bracket 1, 2, 3, 4, 5, 6, CH2, 6, to say there are 6 CH2s in the middle, and then a CH3 at the end. You don't have to do this, you can write it out in each time, but sometimes it can be helpful to know that you can condense it down a little bit like this. Some of you may have been aware enough to work out that this works really easily if everything is in a nice straight line, but what if you've got something sticking out? So if we had, let's say, a displayed formula that was like this, so we have a CH3 sticking out from our main carbon chain, so this would be our main carbon chain, and this one would be sticking out. How would we show that in structural formula? So this carbon belongs to this carbon unit, so we need to show that it's attached somehow. So our first carbon unit we would look at would be our CH3. That would be easy enough. Then our second carbon unit we know is a CH, but it also has another carbon on it. So to show it has another carbon on it, we would put that carbon in brackets to say this carbon unit is attached to this carbon before it. And then we'd have our final carbon unit, CH3, like this. They tend not to ask you too many questions where this may happen, but it's worth knowing that if it's in a bracket with no number after it, it's because it's attached to the carbon before it. That bracket there would be attached. Now, our final type of representation is called a skeletal formula or a skeletal formula. You won't be asked to draw these at this point in GCSE, but you will sometimes encounter things that are drawn in this format. Because it's very quick to draw, particularly when you have big complex molecules, but it shows very little detail. So if you don't know what's going on, you can't really work out what each thing is. So here I have drawn a paracetamol molecule in full displayed formula. It's quite fiddly to draw. So skeletal formula attempts to simplify things down. So we don't draw the carbons anymore. We assume at the end of a line, where a line turns into another line, that there is a carbon, that we have drawn that carbon on. So we can remove all of the carbons like this. So our 6 carbons in a ring here just becomes this hexagon, and we're assuming that there is a carbon at each of these. We can also assume that hydrogens are there to make the bonds add up to 4. So we don't need to draw on these hydrogens here, because we can assume this carbon here currently has 3 bonds, so there must be a hydrogen on it. So we would have to draw the OH on to show that that is there. And attached to this carbon we've got a nitrogen, so we would draw that nitrogen on. And it has a hydrogen, so we would draw the hydrogen. We don't need to draw this carbon because it is a carbon, but we do need to show the oxygen, so we would draw the oxygen. And we don't need to show this carbon, we just draw a line. This end of the line is a carbon, and we don't need to draw the 3 hydrogens on because we assume they are there. So it is a much simplified form, but if you don't know that at the end of each line is a carbon and that you have to add hydrogens on to add up to 4 bonds, this looks completely alien and you would have to work on this. Skeletal formula is not very useful for small molecules. For example, our ones we did, C2H6 would just be a line because there would be a carbon at each end and we wouldn't have to draw on the 6 hydrogens. C3H6 would be 2 lines, a double bond, and 1 line. So don't really need to, that can draw it quick now. C3H8 would just be this. It's better for things like C8H18, but you have to remember there's a carbon at each end. So 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, 8 carbons. So this would be our C8H18 because we assume that it fills up to all of the hydrogens. Don't worry if it's just a little bit confusing. Like I said, you won't ever have to draw these yourselves, but you may have to work out how many carbons are in there or interpret them a little bit if someone's already drawn the diagram for you.